Hi everyone, my name is Len. I work at Intel in our FPGA organization. So if you have questions about CPU or about Spectre, don't ask me any of that. Okay, so my topic today is something to do with jump tables. So a few caveats first, right? First of all, I'm not saying that jump tables are better than linear lookup or bind lookup or whatever. I'm just showing a way to force a compiler to generate jump tables if you want to go and explore whether or not that's going to be a better approach for your particular use case. Because we know there are certain use cases where it's actually better in terms of performance. Uh, another thing, another thing that I want to mention is that that being said, right, there are a few examples that I'm going to show, where compilers do something that is perhaps not doesn't look too good for them. So if there are any compiler, writers in the crowd here, right? So if I'm dead in a ditch tomorrow, you know who to blame. Okay. So that's the introduction. So let's go to the next slide. Okay, so let's just start very simple. Let's just look at a simple lookup table sort of thing. You have an index here, and then depending on index, we return a different value. And on the right, you can see assembly. Pretty standard. This is what we expect. You have just a whole bunch of compare and jump, compare and jump. So pretty simple. This is a linear lookup table, nothing special. So here's the thing. So this is only 3 branches. Let's see what happens if we go and crank it up. You crank up to many, many branches, many indices, and many values. So so in order to do that, we need to first produce values for each index that breaks patterns, that do not have a certain pattern. And the reason why you don't do that is because you want to prevent the compiler from trying to find a pattern and try to flatten everything. Like for example, if your return value is always index +1, then obviously the compiler can figure out that it can just squeeze everything down to 2 lines of assembly. So we don't want that to happen. But to do that, we need to go and again find some way to produce some numbers that are not uniform or has a pattern. So really simple way. Let's try to use Fibonacci because that's something that breaks patterns. So this is a classic way of getting the Fibonacci number by using template specialization. Obviously in C++11, you can do a lot better than this. I can use CodeExpert. But for the sake of argument, let's just go and do this. So one of the things you might note is that the assembly on the right side, we hard-coded 10 there, so it's only returning the Fibonacci value for Fibonacci number 10, which is 55. How do you go and transform this to a table and also be able to pass in a runtime value to look up that table? Really simple. Just go and add operator param and pass an index. So what the key point here is that the operator param will go and compare the runtime index with the I there, which is a comma time value. And then if it's the same, then return the value. Otherwise, delegate to the next specialization to evaluate whether or not the index is equal to the compile time value. Really simple. And then what we do is instead of returning value, we instantiate this and then pass in the runtime value. I use account because I'm lazy, and that's one of the easy ways to do it. So, pretty simple. This is only with 5 numbers. This is what we expect. It's all just going to be a linear lookup table. So nothing special. So the compiler decide that you can just squeeze it in, and the runtime to go through all this that's not significant anyway. But what if we go and turn up the crank? What if we go and generate 500 numbers? Would the compiler go and produce a new list of compare and jumps? Let's take a look. Yes, it does. So it generates all of this, and then let's look at backpage. 1,000 lines of compare and jumps. So what that means is that if you're generating, maybe Fibonacci is a bit contrived, but something a little bit more interesting. And if most times you're passing in a runtime index that is large, you have to go and do this again and again and again, and this is not going to fly in certain applications. So let's talk about something that is, and I'm running out of time. Let's talk about something that's a little bit more practical. Fibonacci is a bit contrived. Let's talk about variance. Right now, all implementation of variant classes, as far as I can tell, standard variant, boost variant 2, perform linear lookup. And just generally fine, as I said, but if your n is large, then you don't want to do it. Obviously, benchmark first, it might be better than a jump table. But what I want to say is that we want the choice to use jump tables if we so choose. So how do we do that? Well, first of all, let's do a proof of concept. maybe hard code everything first. So turns out to be the way to generate jump tables for the compiler jump table. So what I have here is I have 3 functions, and then I shove all these functions with the same signature into a jump table. And then after that, I use index to index into this jump table and call it. So really interesting assembly. Each of the functions has been converted to its own label. And then finally, you have this table over here. Each of them is 8 bytes separated. And then you have this jump here, and takes RDI, which is actually index, multiplied by 8 because pointers in 64-bit machines are 8 bytes. So there we go. So it takes this particular label, the reference RDI times 8, which is one of those things, and then just call it directly. So this is a definition of a jump table in C++. So I'm going to fly through this because I'm out of time. So this is how I go and do it. So we have a variant. You can go and get the type of the variant at a particular compiler time index. And then so for each index, you generate a different function, specialization with a different address, and then shove them all into, using variant template, shove them all into a jump table, and then call it directly. And then finally, you can go and get size, which you can do easily using standard variant size v. And then let's look at assembly. So really simple. You don't even have to go and hard code anything. And so these are each of the callbacks. This is a call table. It's a jump table. And then this is the one call. And that's something on the right, multiplied by 8. And it jumps straight to it. So again, benchmark this. This is not guaranteed to be faster than what the compiler produces in a linear lookup. But at least you have a choice here. And really sneak peek. It's possible to do a compiler time hash map or set. And one of the nice things is that it's perfect cache locality here. Really cool thing. So that's all I have. Thanks, everyone.